Now let's do an example problem together that it will include all the topic we just discovered. Well, first of all, it gives us a chemical equation that is describing this chemical process. And we have different experiments in terms of 1, 2, 3, 4, and that will be your trial. Now we have your initial concentration of A and your initial concentration of B. Notice we don't care about C and D, right? Because reaction rate is based on the concentration of the reactant. Then we also have your initial reaction rate. And with that information, we can actually compare them together to solve for your exponent part in terms of this. So if I were to write the law in terms of this chemical reaction process, of course the rate law would equal to the concentration of A times the concentration of B. But the goal is that we have to figure out what is that number is going to be. Well, you have to do one by one first. To do that, you have to do one reactant at a time. And the goal is to find where the concentration of either B or A stay the same, but one of them is different. So let's look at this problem right there. Determine the order of the reaction with respect to reactant A. So we're going to focus on A. Basically, we are looking at the changes in A in terms of the experiment number. Now, look at this experiment. We have 0.33 and 0.34, that's about the same, okay? But where we have 3 and 4, they are completely different. So we have to use two of them that are different. But we cannot use 4 because we don't know the reaction rate for 4, okay? So we are limited to 2 and 3. Well, turn out 2 and 3, there's a big change. But before we can realize that we can actually use 2 and 3, we have to look at B, or the other one. They have to be the same. Look at that. We have 0.137 and 1.36. So we keep this concentration about the same. That way we can just cancel out the B in the process. So let's look at 2 and 3. What happened? Am I going to put 2 first or 3 first? Well, mathematically, it's better to have a whole number than a fraction. So I'm going to put rate of experiment 3 first versus rate of experiment 2. So in this case, we know that A times B. But B can be cancelled out because they are the same. So let me show that to you. So in this case, A is in terms of concentration of 3 is 0.136. Okay, equal to that number right there. And that is relative to 0.034. Okay, time B, which is 0.136, that's for 3, and that's relative to the number right there, divided by 0.137. Okay, this is about 1, so it's cancel each other out. Now, in terms of the rate, that is referring to the initial rate. Well, are we given the initial rate? Well, yes, right there. That's the reason why we couldn't use 4, because even though there's a changes, well, we cannot use 4 because B changed as well. We cannot use it because one factor is that it doesn't give it to us. Now, let's look at in terms of rate 3. What's rate 3? It's right there. So we have equal to 1.07 times 10 to the negative 2, where for rate 2 is 1.08 times 10 to the negative 2. Well, that negative 2 can cancel out. So it's just 1.07 divided by 1.08, which is about 1, isn't it? So we have this equal to 1, but that's equal to what? 0.136, 0.034, and that gave us a number right there. So can we simplify this number? Well, easily. Let's use a calculator. 0.136 divided by 0.034, that turned out to be 4. So we have 1 equal to 4 to a number. And what does this number has to be? What number has to be for the exponent? Of course, anything to the 0 power is equal to 1. So basically any number equal to 0 power equal to 1. So that tells you that this order must be 0. So we can express that A must be to the 0 power. Right there. So this must be the 0 order. respect to the reactant A. Now, in this question, it's asking us to do in terms of reactant B. And the same process, okay? We need to look where B has changes. So look at B. What happened in B? Here we have here, and that. Oh, look at that. It changed there or there. So we can use 1 and 2 or 1 and 3. That's because it has changes, right? So either 1 and 2 or 1 and 3. Or 1 and 4, but we cannot use 4 because that is not given to us. So which one do we use? To do that, we have to determine, we have to look at A. We need to keep A the same so we can cancel it out. So in this case, with 1 and 2, the A stay about the same. Where 1 and 3, look what happened, the A also changes. So you cannot use 1 and 3 because of the A changes, but we have to be limited to just 1 and 2. Because for B, there's a change, but for A, there's no change. So that way it can cancel out. Again, we are going to put the larger one on top, so that way our fraction is a lot easier. So we're going to have rate of 2 over rate of 1. And of course, the A can cancel out already because we rewrite this right here. We have 0.137 divided by 0.034. And of course, we can group that equal to a number right there, time your A, which is 0.034 divided by 0.033 to the number. But that cancels out equal to 1, okay? And look at in terms of the rate. For rate 2 is equal to 1.08 times 10 to the negative 2. And that is 6.67 times 10 to the negative 4. Now, we can simplify this, okay? So that's an equal sign right there. Can we simplify that? Of course. 0.137 divided by 0.034, we get about 4. Again, because we did want exponent, we had to estimate it, okay? So that is relative to 4 equal to a number. And over here, we just divide it. 1.08 e to the negative 2 divided by 6.67 e to the negative 4. And that gives us about 16. So what number the exponent has to be? Well, 4 to the power of 2 is equal to 16 because 4 times 4 equal to 16. There you go. So what does that tell you? This has to be the second order. And then for C, write the rate law for the overall reaction. We just did that up here already, right? So in this case, what we have is in terms of rate law equal to the concentration of A times the number up there and B times the number up there. And if you are using the chemical, this just be your chemicals in there. That's all it is. But we realize that this from this part right here, that's actually equal to 0. Where this part right here is actually equal to 2. So we can rewrite this A. Oh, A is no longer there anymore. Because anything to the 0 is equal to 1, right? So, well, of course it's K right there. K time to the power of B. And we figured out that is to the second order, so this must be 2 right there. So that's all we have to do. Isn't that easy? So that is your rate law right there. And then we move on to the next problem and say determine the values of the rate constant K for the reaction. Include units with your answer. That's where it gets tricky, okay? Well, in this case, to solve for the K constant, that's pretty easy because you know your rate law already. All you have to do is take this right here and use one of the data and use one of our experiment reaction rate to get our rate. And then we just have to solve for K because we're also given the concentration as well. So let me zoom this out, okay? So what we have here is, choose one. Let's choose the first one. How about that? Let's choose the very first one, which is rate law equal to your rate, which in this case 6.67 times 10 to the negative 4 equal to your K concentration of B. to the power of 2. Can we plug in for B? Pretty easily. It's equal to 0.034. So this can be plugged in with 0.034. And that's coming from the same experimental data, okay? Don't mix with this something else. If you're using that one, then you use that one. If you're using this one, then you have to use that one. So be careful with that. Now, can I solve for K? Well, very easily. All you have to do is divide it. So in this case, 0.67 times 10 to the negative 4 divided by 0.034. But be careful that this is to the second power. So let's plug this into our calculator. 6.67 exp to the negative 4 divided by 0.034 to the second power, and that gives us 0.57, and that can be rounded to 7. And what is the unit gonna be? Remember, we're talking about the rules for finding a unit where m 1 minus the number of order time s to the power of negative 1. So in this case, the order is 2, so m must be what? Negative 1 and time your minus s. And that would be the unit for your k. Isn't that easy? Well, now we find our k, so we can have our rate law right there, which is the term rate equal to k times the concentration of B to the second power. And we know what k is going to be, which we just figured out is equal to 0.577 m minus 1 times s minus 1. So in this question F, it asks you to find the rate for experiment 4, and we notice that experiment 4 in the table is not given to us. So can we just use this data to solve for it? Well, in this case, do we care about the concentration of A? No, because A is not really included in our thing. So what we have here is, for experiment of 4, our rate of 4, we just plug in K, which is 0.577 times the concentration of B to the power, which in this case is B right here, is 0.233, so 0.233 to the power of 2. And that will give us our rate for 4. So plug it into our calculator, 0.577 times 0.233 to the second power, and that will give us 0.031. So the rate is equal to 0.031. And, well, 36, think about that. Okay, fine. And look at the unit. What's the unit going to be? Of course, it's going to be the same thing as the other one, of course, in terms of mole time liter minus 1. There you go. And that's all you have to do. And then for F, I forgot to write it down, but basically it's like this. It gives you this series of reaction and basically telling you that, can we use this series reaction to make your product, basically your overall reaction right there? Well, in order to do that, we have to realize two things. The first thing you have to realize is this. When we combine them together, do they cancel each other out? So I'm going to do that right here. How about that? And we'll talk about that later. So we'll talk about this. So we have, well, in this case, B plus B, that gives you 2B, okay? And plus E plus A, that equal to E plus D plus B plus C. So what happened to the letter E? It got canceled out. What happened to the letter B? That B got canceled out. Give us 1B. And what happened to the letter A? Oh, still there. And still D. So we have B plus A equal to D plus C. Will give us the overall reaction right there. So that proved to us that we can actually use this series of steps to produce your product from the given reactants. And that's all you have to do. Well, now if we look in terms of the rate law for this overall reaction, right? Remember the slowest steps determine the reaction rate law? Well, we look at this in terms of reactant, that is rate log, well, let's put rate equal to K times your reactant, which is B times B. And what do we have? K equal to B squared. And then that will be your other option as well. And then for the next problem, we have to identify if E is a catalyst or an intermediate. First of all, let's look at E. E is produced in the product side right here, and then later on it's being consumed. And E is being canceled out, right? So because it's being produced and it's being used up, that has to be, E must be your intermediate.